Hello and welcome to this section of the Calculus Derivative Help Tutor. In this section we're going to tackle the topic of how to take a derivative of a general exponential and a general logarithm. And what I mean by that is in the last two sections we've done the natural logarithm, which was base e logarithm, and we've done what we call natural exponential, which was an exponential with a base e. So e to the x and logarithm of x. That's what we did in the last two sections. This section we're going to loosen the belt a little bit and get more general, where we can have exponential functions of different bases and we're going to have logarithms of different bases. But what we're going to find is that they're going to be a little bit related to what we've already learned. That's why we learned the special case first. Now we're going to come and learn the more general case. So what do I mean when I say a general exponential? A general exponential is usually written as a to the power of x, where a is a number. Now you might look at this at first glance and say, well, I know how to take the derivative of that. We did that in the very first part of Calculus 1. Well, not really. What we did in the first part of Calculus 1 was x squared. That's variable on the bottom, exponent on the top. That's not what we have here. Here we have something more like 2 to the power of x, where a is any number you want to pick. It could be 3 to the power of x, 15 to the power of x, negative 2 to the power of x, whatever. But it's different because here we have x to the power of a number, and here we have a number to the power of x. This is what we're studying in this section. We have not learned how to take the derivative of that function yet. We've learned how to take x squared, x cubed, x to the fifth. We've never learned how to take 2 to the power of x or 3 to the power of x. So that's what we're going to be doing here. So this is an exponential. Now the derivative I'm just going to write down without proof, and then we'll work a lot of problems just like we did in the last section. So the derivative with respect to x of the function a to the power of x, where remember a can be any number you really want it to be, is equal to a to the x, okay, times natural log of a. So here we have, let me draw some parallels. The derivative of this general exponential yields the same exponential back. So it is indestructible to a degree, just like the regular e to the x function was indestructible, right, when we take a derivative. The only difference is we have a modifier. We multiply by the natural log of whatever this base number is. So that's the only real thing that's changing it. It stays indestructible, but we multiply it by natural log of the base. Now, if this were e to the x, let's do a little aside here. If it were e to the x, and we were going to use this rule to apply to it, it should work, right? Because this is just another number, just like any number we can put in here. Then we would have the same exponential left over, or I should say e to the power of x, because it's indestructible, multiplied by natural log of the base, which is natural log of e. What is natural log of e? Natural log of e is 1, because e raised to the power of what number is going to give me e? Well, e raised to the 1 power is e, so it's going to be 1. So it's going to give us e to the x back. So this is the more general formula. This is the exponential derivative formula that applies to all exponential functions. Whatever number we have for a, we just keep the function indestructible and multiply by natural log of the base. It just so happens that when you have a natural exponential function with a base e, then when you apply this, this just goes to 1. So it's just indestructible, by itself over and over and over again. So we learned the special case first in the last section. Now we're opening our eyes a little bit to the more broad case. So 2 to the power of x, 3 to the power of x, 10 power to the x, we're all going to apply this guy. It's just that when we have e to the x, it just so happens that this term drops out to 1. Okay? So that really is almost half of what I want to teach you in this section, is how to take a derivative of an exponential function when the base is any number that you want. We'll work a lot of problems and show you how to do that. Now, what about a general logarithm? A general log, which might be something like log base a of the number x. So we've talked about natural log, right? We've talked and learned about how to take the derivative of those guys. It's just 1 over x. That's a very special logarithm where the base here is e. That's that very special guy. Here is the more general logarithm where it could be base 10 or which is your button on the calculator, or base 9, or base 3, or whatever. It just means that when you take a log like that, it's going to be the base raised to the power of some number is going to try to give me x back. That's what a logarithm is. How do we take a derivative of something like this? Well, you really don't do it directly. What you do is you rewrite it. You rewrite it as the following thing that we know how to take the derivative of. We rewrite this logarithm. Let me change colors here. We rewrite this log as log of a, or base a, of the number x is equal to natural log of x over natural log of a. So it's natural log of whatever you have here divided by natural log of whatever base you have here. This is something that's not going to be proven to you. I'm not going to prove this to you. I'm going to expect you to know this, and your teacher's going to expect you to know this. These are two extremely important things, and look at what we've done here. This is something that's been proven ahead of time. There is a proof in a book somewhere that will prove to you that if you take any old logarithm, you can write any logarithm in terms of the natural logarithm function. And that's just another proof why the natural log function is so special, that you can take any log you want, base 94, and it will be natural log of x divided by natural log of 94. This bottom number is just a number. Natural log of the base is literally going to give you a number back. The top is natural log function. We know how to take the derivative of natural log functions. So really, once you rewrite it like this, you can use the regular rules of differentiation to take this derivative. This bottom thing is just a number. It comes out. The derivative of the top, we've just done an entire section on how to do that before. So anytime you see a logarithm written like this with an arbitrary base, just rewrite it like this. It's a good identity for you to know. Don't get wrapped up too much if you don't understand why this is the case. It's kind of like a lot of trig identities, you know? You can go roll up your sleeves and try to learn why all those trig identities are true, but ultimately, at some point you just have to accept that someone has proven that they are true, and you're just going to use them to go forward and you know, better your own knowledge and try to contribute yourself and learn about science and engineering using those results. This is something that's been proven to be true, so we're just going to use it. Okay, now here's some other things that are going to be helpful in this section. Other useful properties. Other useful properties. What I mean by that is other useful properties of logs and exponentials. Basically, a lot of these functions are going to really be benefited if you can rewrite them in terms, just like we were rewriting this one, if you can rewrite them in another form. Here's the first one. I'll put a little star by it. Actually, let me just put a number by it. Here's the first guy. If you take the natural log of this arbitrary exponential a to the power of r, I could make it a to the power of x, doesn't matter, then it's exactly the same thing as taking this r out, multiplying by natural log of the base. This is really a property of logarithms, and all of these things that we're going to list here is really just property of logs. You've probably learned them in an algebra class or learned them in a trig class or a pre-calculus class. This is sort of a refresher for you because you're going to use these things to manipulate these functions prior to taking a derivative. But anytime you have a natural log and you have an exponential on the inside, where it's a number raised to a variable like this, then you can just take the variable on the outside, or take the exponent on the outside of this logarithm. It's just something that's proven to be true. And that can be quite useful when you're taking derivatives, so that's why we're listing it here. Now, related to this, if I take this equation, because this is an equation, these two things are equal to each other. If I raise both sides, right, of this guy to the power of e, if I raise the left side, e to the power of natural log of this stuff, then I told you before from the last couple of sections that the e and natural log are inverses of one another, so they'll cancel. So what you'll be left with is a to the r on the left, and on the right you'll have e to the r natural log of a. So this is another very useful identity that we can use a lot. If we just see an exponent sitting, or an exponential like this sitting by itself, we can rewrite it as e raised to the power of r ln of a. I know that you don't see why this is useful yet. That's okay. I need to present these things so that we can get to the problems and you can see how it's useful. Where does this come from? It comes from directly above. If I raise the left side, e raised to the left side of this guy, the natural log is going to disappear. I'm going to be left with this. The right side raised to e is going to give me this. So it really follows from number one. Number three, if I have f of x, which is some function, raised to the power of g of x. So a function raised to the power of a function. then I can rewrite this as e to the natural log of this function raised to this function. This should not surprise you because when you take an e and you raise it to the power of a natural log with something here, the e and the natural logs kind of annihilate each other, and what you're left with is everything that's up here, which is what I have over here. It's nothing more than that. They're inverses of one another. So e raised to the power of natural log is going to basically fall out and annihilate, and what you're going to be left with is what's going to be in the top. But the reason why it's useful is because if we look at the top here and realize at the top in the exponent we have a natural log of something raised to something else. Natural log of something raised to something else. So I can further rewrite this as e to the g of x times natural log of f of x. Because this exponent up here is just nothing more than what I have written here. So I can take this exponent down in front. So I take the g of x down in front of the natural log. I could have not even put this on the board and said this is equal to this, but it would have been a little bit harder for you to see where it comes from. Basically, you can rewrite it this way because you can say e raised to the natural log of what I have, that's equivalent, and then I can use this little fact to pull this exponent out. So this guy, going from here to here, we're going to use for almost every problem written like this. This kind of guy might be something like, when you have a function raised to the power of a function, might be, instead of sine squared, sine to the power of x, or sine x, the entire thing raised to the power of x, or x raised to the power of sine of x, or x raised to the power of a logarithm of x. Anytime you have some function of x raised to the power of another function of x, it's going to be super beneficial to rewrite it like this, and you'll see why later. I don't expect you to see that now. I just want you to list these things so that when we use them, you won't be like, well, what's he talking about? And finally, this is just a property of logs that you probably already know. Log of a of b times c, so two numbers multiplied together with a base a logarithm, is equal to the log base a of b plus the log base a of c. So basically, if you have a logarithm of two things multiplied together, you just add the logs of the two things together. So, big picture, we're going to work a lot of problems here, and I want to quickly review what we've written. When you have the derivative of an exponential function with an arbitrary base, you keep it as indestructible, but you multiply by the natural log of the base. That's it. If you have a general logarithm that you want to take the derivative of, then you rewrite it in terms of a natural log of the variable over the natural log of the base. We know how to take the derivative of this, so then we'll do that. And finally, if we have natural log of some exponent, we can always pull the exponent out in front of the natural log. And directly following from that, we can write any exponential like this as e to the r natural log of the base. And we'll see why that's useful in problems to come. If we have a function raised to the power of another function, like t raised to the power of natural log x, for instance, it's better to go ahead and rewrite it. You can see the intermediate step, but the end result is going to be this, which is useful, that we can raise it as e raised to the power of this top function out in front of the logarithm of the other guy. And then we have the sum of the logarithms the little rule of logarithms we have in the bottom. So you might look at this and your eyes might glaze over and like, oh my gosh, this is crazy. But really it comes down to working a lot of problems and seeing how to apply it all. If you just do this, like your book will show you, you'll probably be completely lost. So let's go ahead and fix that by working some problems. So first concrete problem, f of x is equal to 5 to the power of x. So that's probably the simplest problem I could come up with. If it were x to the 5th power, you would know how to do it from the very first section here. You know how to do a regular like polynomial type of deal. But this is not the case. It's 5 to the power of x, which follows this guy. So it's number raised to the power of a variable. So what we do is we keep it as indestructible, but we have to multiply it by a modifier. So f prime is equal to, we keep it as indestructible, but we have to multiply it by the logarithm of the base, ln of 5. You stop there because there's nothing else to there's nothing else more complicated up here that you would have to multiply using the chain rule. So ultimately, the final answer is ln of 5. That's a number. You can just get that number in your calculator, times 5 to the power of x, and that's the final answer. That's how you would take the derivative of 5 raised to the power of x. Now let's make it a little more complicated. Let's say we had f of x is equal to 3 to the power of 5x minus 7. So here it's a little more complicated. We have a number raised to something, but this something is not quite as simple as what we had here. So we're going to need to use the chain rule in addition to what we already know from this section. So f prime of x is equal to. Well, the big picture, the outer function, is it's a number raised to a function, so we keep that as indestructible, 5x minus 7. But we have to multiply by natural log of 3 because that's our general rule. That's the derivative of the general deal. But we can't stop there because this exponent is more complicated, so we have to multiply by the derivative of the exponent, which is just 5. Right, because it's 5x minus 7, take that derivative. So ultimately, this final answer, f prime of x, is equal to 5 times natural log of 3, let me go ahead and put parentheses around here to make it clear, times 3 to the 5x minus 7. And this is the final answer, 5 natural log of 3 times 3 to the 5x minus 7. Now, 5 natural log of 3 is just a number. I mean, that's just a constant. You can get out of your calculator once you take the natural log and multiply by 5. So you have a number out in front of this guy right here. Okay? Now, for the third problem, we'll ratchet up the complexity just a little bit. What if we have a to the power of x times the sine of bx, where a is just a constant, is a number, and b is also a constant, it's just a number. Well, the first thing you should notice is that we have two functions multiplied by one another. We have this a to the x function, and we have this sine function. So they're multiplied together, so we need to use the product rule. So g prime of x is equal to first times the derivative of the second plus the second times the derivative of the first. So what we'll have is a to the power of x times, to keep it clear, let's write it explicitly, sine of bx, we'll take the derivative later, first times the derivative of the second plus the second sine of bx times the derivative of the first, that's a to the x, and we'll take its derivative here in just a second. So let's go ahead and take these derivatives. G prime of x is equal to a to the x. What is the derivative of this? Derivative of sine is cosine. We keep the argument the same, bx, but we have to multiply by the derivative of the inside. So this is a constant, it's a number in front of x, so it's just going to be b, that's its derivative, plus the sine of bx. What is the derivative of this guy, a to the x? Well, if we look over here, the derivative of any exponential like this is we keep it indestructible times natural log of the base. So it's going to be a to the x times natural log of the base. And that's it. It's not any more complicated than that because this exponent really is x, so it comes straight off the board. So the final answer, g prime of x, is equal to, we have a b here, so we'll keep it as b times a to the x times cosine of bx, right? Plus, here we have a to the x ln of a times the sine of bx. And let's just make sure that's right. We have b a to the x cosine bx plus a to the x natural log of a times sine of bx. Looks super duper complicated, right? But it's just a matter of plowing through it. First times derivative of second plus second times derivative of first. And just being methodical, showing all of your steps to make sure that you don't get into trouble. All right. Now the next step, the next problem is going to change gears a little bit. G of x is equal to x times the log base 2 of x. So here we have two things going on. We have a function x here multiplied by another function, which is this logarithm, but this logarithm is not a natural log or a base 10 log even, it's a base 2 log. So when we look back at our little sheet here, when we have anything like this, we rewrite it as natural log of x over natural log of a. So that's the very, very first step before you take any derivatives. It's kind of like when I always tell you to rewrite those square roots as with a fractional exponent. It just helps you. So you need to do that here. So g of x is equal to x times natural log of x over natural log of 2. That's how this works, right? So this is the function we need to take the derivative of. Now don't forget, natural log of 2 is just a constant. It's nothing fancy. So when we take this derivative, right, let's let's go ahead and take it one step at a time. We have two functions multiplied by one another. We have this function times this larger one here. So let's go ahead and do that. We'll have first times the derivative of the second function plus the second function times the derivative of the first function. And we just go in order. So g prime x is equal to x times. What is the derivative of this? Well, this is just a number on the bottom. So what you really have here is 1 over natural log of 2. That kind of comes out. And then you have the derivative of this guy, which is just 1 over x. So you have 1 over x here. Make sure you understand that, because you have 1 over natural log of 2 is going to sort of, you can pull it off to the side to make everything clear. And then you have the derivative of this guy, which is 1 over x. Okay, plus natural log of x, natural log of 2. What is the derivative of this guy? It's just 1. So that is really the answer, and you can sort of circle that if you really wanted to. G prime of x is equal to, x is going to cancel with this, so what you're going to have is 1 over natural log of 2 plus natural log of x over natural log of 2. Now you could circle this. This is perfectly fine to leave as your final answer. However, look at what we have here. Natural log of x over natural log of 2. Does that look familiar? Natural log of x over natural log of a number. We can rewrite that as a logarithm. It's not something you have to do, but, you know, why not? 1 over natural log of 2. We can rewrite this as log, not natural log, log base 2 of x, because this is equal to this. And then it's a little bit more simplified. And also, your original problem was in terms of base 2 logarithm, so it's kind of nice when you can to write your answer in terms of base 2 log, if you can. It's not something you have to do. It's not something that I would even say you would get points off on a test if you left it like this, but it's something that you can do. Okay, the next problem is, let's say we have y is equal to t raised to the power of t. We want to take that derivative. Now this is something unlike we've really ever learned how to do before. We haven't learned how to take, until this section, how to take a derivative of a function when you raise it to the power of another function. So when you think back, you've learned t squared, logarithm of t, sine of t, tangent of t, secant of t, square root of t, and all that stuff. But you haven't learned t raised to the power of t. That's different. So we go back to our board and we look down and we say, well, function raised to a power of function. This is where we're going to get into where this is very useful. So basically we can rewrite this function as, I'll go ahead and do it in 2 steps to kind of show you where it comes from, but you know, we'll kind of skip along a little bit in the subsequent problems. This is the same as e raised to the power of the natural log of t raised to the power of t. When you think about it, since e annihilates natural log, when you do this, it basically, they disappear. So this really and truly is equal to what I've written on the right-hand side. And also, in the numerator, I'm sorry, not the numerator, the exponent up here in the top, I have natural log of t to the power of t. Well, I have a power inside of a natural log. I can pull the power out in front. So what I'm going to really have up here is t times the natural log of t, which is really what I'm trying to write here. E to the t natural log of t, which for this problem is what we have over here. Now in the future problems, we might not explicitly show this step, but I really want to show you where it comes from. We're not working magic here. We're just using the properties of logarithms and exponentials to get there. Now, why is this good? Let's go and take the derivative. Y prime is equal to, well, this is an exponential function. It's indestructible. So we can just rewrite it as e to the t natural log of t. But we can't stop there because we have to multiply by the derivative of the exponent up here, which is a product of these two things. So you have to multiply those things. So it's going to be t multiplied by the derivative of the second guy, which is 1 over t, plus the second guy, natural log of t, multiplied by the derivative of the first, which is 1. Make absolutely sure you understand where I'm going with this. If I, in a lengthy problem like this, if I write everything out too much, it actually clutters things up a little bit. So I don't want to say I'm skipping steps, but I am kind of combining steps a little bit. So here, this is the indestructible. What's inside here is the derivative of the exponent. This is a product. It's first times derivative of the second plus the second times the derivative of the first. First times the derivative of the second plus the second times the derivative of the first. I'm just doing the derivative in the step there, because if you write it out too much, it can actually get kind of confusing. t is going to cancel with t. I should say it leaves 1 behind. So y prime is going to be equal to e to the t natural log of t. And on the inside here, I'm going to have 1 plus natural log of t. Okay, now I'm almost down to the answer. What am I going to have here? E to the t natural log of t is exactly the same thing, I think you can convince yourself, as what I started with, t to the power of t. This is equal to this because I can move this guy right back into the exponent, just like I can pull it out, I can put it back in there. That's a property of logs. So it's t to the power of t. E is going to cancel with this natural log, so here I go. And here I'm going to have 1 plus natural log of t. And this is the final answer. So t to the t times 1 plus natural log of t. It's kind of a hopeless problem to do unless you understand these little simplifying things. What it basically boils down to is anytime you have a function raised to a function, you rewrite it as e to the exponent of your function times the natural log of the lower part of the function there. The reason you do that is because the exponential is very easy to take a derivative of. That's really the bottom line. You keep it indestructible, you multiply by the derivative of the exponent, that all falls out, and then you get the answer. Because this can be converted back into this function that you started with. Okay, let's do another one. Let's say we have y is equal to t to the power of 2 over t. So it's a similar kind of deal, except I've got a function raised to power function. It's just that this guy in the top is kind of uglier because it's a fractional thing. But what you really need to do is the same as before. You really need to rewrite it. So let's rewrite it as e to the 2 over t natural log of t. This is the same as this. It's exactly equivalent. If you graph this and you graph this, they will look identical. Because this 2 over t can be put in here, in the exponent of this guy, and the natural log and the e cancel each other. So I get back exactly what I've started with. And that comes straight off of one of these identities. Now when I take the derivative, the reason it's useful is the exponential part stays indestructible. 2 over t natural log of t. And then I just need to multiply by the derivative of this up in the exponent. So I have two things multiplied together, this and the natural log. So I need to use the product rule. So it's going to be 2 over t times the derivative of natural log of t, which is 1 over t, plus natural log of t times the derivative of this. But this is, go over to the side here, this is 2 over t, which is 2t to the negative 1. So if I take the derivative of it, 2t to the negative 1, I'm going to get negative 2t to the negative 2. I always do derivatives in terms of powers. It's so much easier. So when I rewrite it like this, it's negative 2 times t, subtract 1 off the exponent. So this guy is going to be negative 2t to the negative 2. Make sure you understand this. First times the derivative of the second, plus the second times the derivative of the first. Okay, so what I'm going to have is going to be e to the 2 over t, natural log of t. And on the inside here, I'm going to have 2 over t squared minus, from here, 2, let me go ahead and rewrite it like this, minus 2 on the top over t squared. I'm moving this guy to the denominator. And I'm going to have natural log of t up here in the top. Make sure you understand this. So 2 over t squared is pretty straightforward. The minus comes from here. The 2 is on the top. The natural log is on the top. The bottom gets a t squared because it's negative, so I make it positive. And then to write the final answer, why did I write y to the t? This is y prime here. So y prime is equal to, outside here I have e to the power of this stuff. That can be converted back to the t to the 2 over t, because this can be moved back into the exponent. Natural log can cancel with e, so you convert it back at the end of your problem. Open this guy. I have a common denominator here now. So I can easily subtract these two fractions, 2 natural log of t over t squared. Okay, and this is the final answer. So I have t to the 2 over t power times 2 minus 2 natural log of t over t squared. So looks complicated, but really it's really only a few lines. The real trick of it is for you to know how to convert this guy to this form and to be comfortable with the derivative of the exponential function and the derivative of the logarithm function, and to know the product rule along the way, because you have to know all of those things. If you're lacking in any one of the knowledge of this of those areas, then even though it's only 3 lines of a problem, you'll have absolutely no idea where to begin. Okay, for our next problem, we have f of x is equal to cosine of x raised to the power of cosine of x. So that's a crazy looking function, but I have function raised to a power of a function, so I'm going to rewrite it as e to the cosine x natural log of cosine x. And if you're confused why that works, it comes straight off the board. This cosine can be moved to the power. The natural log and the e annihilate, giving me back exactly what I started. So those two things are exactly equivalent. If I graph this and I graph this, they're the same. In fact, I encourage you to do that. Grab a graphing calculator and graph both of those things. You'll see that they're exactly the same. Okay, so let's take the derivative, f prime of x. It's an exponential, so it's indestructible. So let's leave it alone for now. Cosine of x times natural log of cosine x. Okay, but I multiply by the derivative of the top, which is a little bit complicated because I have cosine, which is one function, times this natural log, which is another. So I need to use the product rule. So it's the first times the derivative of the second, so it's cosine of x times the derivative of this. What's the derivative of the second function? Well, you got to use your knowledge of natural logs. The derivative of this guy is 1 over cosine of x, but I can't stop there. I got to take the derivative of the inside. Derivative of cosine is negative sine of x. Make sure you understand what this is. So I'm doing quotient, I'm doing product rule. First times derivative of the second guy. The derivative of this is 1 over this times the derivative of the inside, which is this. So that takes care of first times the derivative of the second. Now I have to add plus the second, natural log of cosine of x, times the derivative of the first. Derivative of cosine is negative sine. That part was pretty easy. All right. Next, when we do this guy, f prime of x, I'm kind of, to the point where I've done the derivative, so I can convert this back. This is going to be cosine of x raised to the power of cosine of x, because I can move this back in here and these guys annihilate and I'm left with what I started with. And then on the inside here, the cosine cancels with the cosine, right? So what I'm going to have is negative sine of x from here minus sine of x times the natural log of cosine of x. And again, this is the answer. You could subtract, you could circle that, but just to tidy it up a little bit, what we'll do is we'll pull out a sine of x. Actually, we'll pull out a negative sine of x. So we'll make it negative sine of x cosine of x to the power of cosine of x. And then we'll open this bracket and we'll make it 1 plus natural log of cosine x. So all we did here is we pulled out this. So this multiplied in will give me this. This multiplied to here will give me this. So the answer is negative sine x cosine to the power of cosine. To make that a little bit clearer, you can do it like this. And then 1 plus natural log of cosine x. That's, it's kind of a monster answer, but really you've got a monster function and that's why it happens that way. Now you see why, even though this looks kind of ridiculous to do this, that it actually helps. It's because the derivative of these natural exponential functions are quite easy to calculate. Even though it looks like a lot of steps, it's actually not that bad. Okay, our next question is f of x is equal to 2x to the power of square root of 2. We want to take the derivative. Now first you might look at this because we're doing a lot of problems with exponentials and try to start applying what we've done. But a lot of times in a test your teacher might throw something like this in to kind of confuse you. You actually already know how to do this even before this lesson. This is nothing complicated because the square root of 2, even though it looks funny, it's just a number. And this is basically some stuff in here raised to this power of a number. You learned this a long time ago. You don't even have to use logarithms or exponentials or anything to solve this guy. The way you do it is f of x, you take the exponent down, square root of 2 times 2x square root of 2 minus 1. You subtract 1 off of the exponent, just like x squared. 2 comes down, subtract 1 off of the exponent, and then you have to multiply by the derivative of the inside, which is 2. So the answer to this problem, f prime of x is 2 times the square root of 2 times 2x to the power of square root of 2 minus 1. And I just threw this in here to keep you on your toes to make sure that you're not trying to apply some silly things. So you only really need to worry about this stuff, the stuff in this section over here, when you have a number raised to a power of x. Final problem, g of x is equal to log base 3 of x squared plus 4. So anytime you have a logarithm to a base other than e, you need to come back and apply this identity right here. So we're going to rewrite it right out of the gate. G of x is equal to log, actually what we're going to do is make it natural log of what's inside here, x squared plus 4 over natural log of 3. Make sure you understand this. You just take the natural log of what's over here. In this case, it's x, but if it's anything other than x, you stick it up there, divided by natural log of the base. That's exactly what I have. And we know how to take the derivative of this, believe it or not, because what we have on the bottom is just simply a number. So g prime of x is going to be equal to, we take 1 over natural log of 3 out because it's just basically it's a number, right? And then we start taking the derivative of this guy. What's the derivative of this natural log guy? Well, the outer function is the natural log, so it's 1 over x squared plus 4. But we can't stop there. We have to multiply by the derivative of the inside, which is 2x. And this is essentially it. So the final answer is g prime of x is equal to 2x over natural log of 3 times 1 over x squared plus 4. And that's the final answer. 2x over natural log of 3 times 1 over x squared plus 4. Anytime you see a constant in the bottom, it's just like, think about 3x squared. Take the derivative of 3x squared. The 3 kind of sits there. You take the derivative of x squared, that gives you 2x, and you end up multiplying the coefficients that are on the outside. So this is exactly the same thing. When you have something on the bottom, it's 1 over this guy multiplied by this. So this can just kind of come out. It's just a constant that sits there. Now I just take the derivative of everything else. The derivative of this is 1 over the argument times the derivative of the argument. You simplify and you have the answer. So that concludes taking the derivative of exponential functions and logarithm functions when they're general, when they're not base e. And you'll see that there's a whole host of simplifications and identities and things that are going to help you along the way, and I hope that these problems have really opened your eyes and given you some practice with how to actually apply them. It's not hard, but it is a little bit tedious, and you definitely have to know the rules of calculus from the chain rule and the product rule and the quotient rule and everything else we've learned in order to be good at this stuff. Now, not only does this conclude this section, this concludes this entire course. It's been a great fun, actually, going back and revisiting this material and rolling up my sleeves and giving you just a ton of extra example problems. I do want to go ahead and say that this is a complementary DVD to the Calculus 1 and 2 Tutor DVD that's already out, that's been out for a few years. There are some topics in this course that I was able to cover that I couldn't cover in the other one, and likewise there are some topics in the other DVD that aren't on this. So they are intended to be used together, but most of all what I really wanted to do was take the core topics of calculus, the chain rule, the product rule, implicit differentiation, some of these other things, especially related rates, and really dive in and just do a ton of problems, even more than I was able to do in the last DVD. So if you're watching this and you're still finding that there's some other topics that you need to know for your test, then you definitely need to get the Calculus 1 and 2 Tutor. It's already out, and so hopefully you already have that. If you don't, you can go take a look at that. But in any case, I hope that this DVD has helped you really get really good at taking derivatives. You should pat yourself on the back because that's basically half of Calculus 1 is learning how to take derivatives well. Doing integration is covered on the Calculus 1 and 2 Tutor also. That's the other half of Calculus 1, and that's a whole other challenge by itself. But I hope that I've helped you learn how to take derivatives. I'm Jason with MathTutorDVD.com. Practice your problems. Make sure you know how to do all of these problems. Go back to your textbook, work lots and lots of extra problems, check your work. The only way you get good at calculus is to practice. So do yourself a favor and practice, and I promise you that your skills will improve and your grades will improve.